Tonight, we're going to explore one of the most fundamental aspects of reality, gravity. You experience it every single moment of your life. It keeps your feet on the ground. It keeps the atmosphere around Earth. It keeps Earth orbiting the Sun. It governs the motion of galaxies billions of light years away. And here's the twist that's going to change how you see the universe. Gravity isn't actually a force at all. It's something far stranger and more beautiful than that. Before we dive in, if you find this exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin this journey into understanding what gravity really is. Consider what you think you know about gravity. You drop an object and it falls down. Simple, right? You've been told since childhood that Earth's gravity pulls things toward the ground. That gravity is a force pulling you downward. That the Sun's gravity pulls Earth into orbit around it. Most people believe exactly that. Schools teach exactly that. And while it's not exactly wrong, it's incomplete. It's like saying the Earth is flat because it looks flat when you're standing on it. It works for everyday purposes, but it misses the deeper truth. Isaac Newton figured out the mathematics of gravity in 1687 when he published his book Mathematical Principles of Natural Philosophy, usually just called the Principia, one of the most important scientific works ever written. Before Newton, ideas about why things fell or why planets moved were mostly philosophical guesses. Newton changed everything. He showed that the same force that makes an apple fall from a tree also keeps the moon orbiting Earth and Earth orbiting the sun. Revolutionary because people thought the heavens and Earth operated under completely different rules. Newton unified them with one set of mathematical laws. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Let me break that down. Earth, and you pull on each other hard because Earth is massive. You and a pencil across the room also pull on each other, but so weakly you'd never notice it. Exactly how weak are we talking? If you tried to build a gravitational wave-style detector sensitive enough to register a single person walking past the lab, the two arms of the interferometer would need to be roughly the distance from our star to Saturn. Approximately 10 billion kilometers, or 6 billion miles long. Anything shorter, and the signal is completely swamped by quantum and thermal noise. That's why you can feel the tiniest magnet or a static shock from a doorknob, yet two people standing a meter apart attract each other gravitationally by less than the weight of a single bacterium. Gravity is 39 orders of magnitude weaker than the electromagnetic force on everyday scales. One of the deepest unsolved mysteries in physics, and that's before we even get to the inverse square law. Double the distance, and the pull doesn't halve, it drops to a quarter. Triple the distance, and it falls to 1/9. That's what makes gravity dominate only when the masses get truly enormous. Newton's equations worked beautifully. They could predict the motion of planets with incredible accuracy. They explained tides, the ocean rising and falling because of the moon's gravity pulling on the water. They explained why planets farther from our star move slower in their orbits. They allowed scientists to discover new planets by observing tiny irregularities in the orbits of known planets. That's how Neptune was discovered in 1846. Astronomers noticed that Uranus wasn't moving exactly as Newton's equations predicted. They calculated where an unknown planet would need to be to cause those deviations. They pointed their telescopes at that spot, and there was Neptune. right where the math said it should be. For over 200 years, Newton's laws were considered the final word on gravity. But there were small problems. The most famous was Mercury's orbit. Mercury orbits in an ellipse that slowly rotates over time, called precession. Newton's equations predicted how much Mercury should precess based on other planets' gravity. But the observations didn't match. Mercury was precessing roughly 43 arcseconds per century more than predicted. That's approximately 1/80th of a degree per century. Incredibly small, but real and measurable. Scientists searched for explanations. Maybe an undiscovered planet called Vulcan was pulling on Mercury. It didn't exist. Maybe Newton's laws needed adjustment. Nothing worked. The mystery remained unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein's insight was radical. Gravity isn't a force at all. Rather, it's a curvature of space-time itself. That probably sounds like meaningless word salad. Curvature of space-time. What does that even mean? Let me explain it step by step, building up from concepts you already understand. First, consider space and time separately, the way we normally think about them. Space is the three-dimensional arena where things exist and move. You can move forward and backward, left and right, up and down. Those are your three dimensions of space. Time is different. It flows in one direction from past to future. You experience events in a sequence. You can't move backward in time or jump forward arbitrarily. Space and time seem fundamentally different. Space is where things happen. Time is when they happen. But Einstein showed that space and time are not separate. They're woven together into a single four-dimensional fabric called spacetime. Not just a mathematical trick, a description of physical reality. You can't have space without time, or time without space. They're aspects of the same thing. When you move through space, you also move through time. When time passes, you're also moving through space-time, even if you're sitting still in space. Every event in the universe happens at a specific location in space-time. Not just space and time separately, but space-time as a unified four-dimensional structure. Here's where it gets interesting. Space-time is not rigid. It's flexible. It can bend and curve. And what causes it to curve? Mass and energy. Any object with mass or energy curves the space-time around it. The more massive the object, the more it curves space-time. Earth curves space-time around it. Our star curves space-time much more because it's much more massive. Even you curve space-time a tiny amount. Everything with mass or energy curves space-time to some degree. Think of space-time like a stretched rubber sheet. If you place a bowling ball on the sheet, it creates a dip or depression. The heavier the ball, the deeper the dip. If you roll a marble near the bowling ball, the marble doesn't travel in a straight line. It curves toward the bowling ball, following the slope of the depression. From the marble's perspective, it's just following the straightest path available. But because the sheet is curved, that path curves toward the bowling ball. Similarly, Earth curves space-time around it. When you drop a ball, the ball isn't being pulled by a force. It's following the straightest possible path through curved space-time. That path happens to curve toward Earth's center. The analogy has limitations. The rubber sheet is a two-dimensional surface, being bent in a third dimension. But space-time is four-dimensional, and it's not bending into some higher dimension. It's intrinsically curved, meaning the curvature is a property of space-time itself, not a bending into something else. Also, in the rubber sheet analogy, we're using gravity itself to make the ball sink into the sheet. That's circular reasoning when we're trying to explain gravity. So the analogy is useful for visualization, but don't take it too literally. What does it mean for space-time to be curved? The rules of geometry are different. In flat space, the shortest distance between 2 points is a straight line. But in curved space, straight lines don't exist in the usual sense. Instead, there are geodesics, the paths that represent the shortest distance between 2 points in that curved space. On Earth's surface, which is curved, the shortest path between 2 cities isn't a straight line through the air if you had to stay on the surface. It's a curve following what's called a Great Circle route. Flights from New York to Tokyo fly over Alaska. It looks like a strange curved path on a flat map, but on a globe, it's actually the shortest route. In curved space-time, objects follow geodesics. A planet orbiting our star isn't being pulled by a force. It's following a geodesic through the curved space-time created by the stellar mass. From the planet's perspective, it's moving in a straight line. But because space-time is curved, that straight line from our perspective looks like an orbit. The planet is constantly falling toward our star, but also moving sideways fast enough that it keeps missing it. A perpetual state of free fall. This explains why astronauts in orbit around Earth experience weightlessness. They're not beyond Earth's gravity. The gravitational field at the altitude of the International Space Station, which orbits roughly 400 kilometers, or approximately 250 miles above Earth, is still around 90% as strong as it is on the ground. The astronauts feel weightless, not because there's no gravity, but because they're in freefall. They're following a geodesic through curved spacetime. Earth curves spacetime, and the space station follows that curvature, constantly falling toward Earth, but moving sideways fast enough to keep missing it. The astronauts inside are falling at the same rate as the space station, so relative to the station, they float. You experience the same thing when you jump. For the brief moment you're in the air, you're in free fall. You're weightless. You don't feel your weight pressing down on your feet. Of course, the moment is so brief, you don't really notice it. But if you could somehow extend that moment, remove the ground so you kept falling, you'd feel exactly what astronauts feel in orbit. True weightlessness. Picture yourself in an elevator and someone cuts the cable. Terrible scenario, but stick with me. As the elevator falls, you'd float inside it. You wouldn't feel your weight. You'd be in free fall along with the elevator. Alternatively, imagine you're out in deep space far from any planet or star. You and the elevator are drifting. You'd also float inside because there's nothing to push against. Einstein's insight. These two situations are equivalent. Free fall in a gravitational field and floating in deep space with no gravity are the same experience. You can't tell the difference from inside the elevator. The equivalence principle. One of the foundational ideas of general relativity. Similarly, standing in an elevator on Earth, you feel the floor pushing up on your feet. That's what weight is, the floor resisting your tendency to follow a geodesic through curved spacetime. In a rocket in deep space, far from any planets or stars, if the rocket is accelerating at 9.8 meters per second squared, roughly 32 feet per second squared, the same acceleration you experience from Earth's gravity, you'd feel the floor of the rocket pushing up on your feet in exactly the same way. From inside the rocket, there's no experiment you could do to tell whether you're standing on Earth or accelerating in deep space. These two situations are equivalent. The equivalence principle leads to some strange predictions. One is gravitational time dilation. Time passes at different rates, depending on where you are in a gravitational field. The stronger the gravitational field, the slower time passes. If you're standing on the surface of a massive planet where space-time is highly curved, time passes more slowly for you than for someone in orbit where space-time is less curved. Not a perceptual thing. Not that time feels slower. Time actually passes at different rates. If you had two synchronized clocks and put one on the surface and one in orbit, when you brought them back together, they'd show different times. The one on the surface would show less time had passed, measured experimentally many times. In 1971, scientists put extremely accurate atomic clocks on commercial airplanes and flew them around the world. When they landed, those clocks were ahead of identical clocks that stayed on the ground by exactly the amount predicted by general relativity. The difference was tiny, measured in nanoseconds, but it was real and measurable. GPS satellites orbiting Earth have to account for time dilation, or their position calculations would be off by kilometers within hours. The atomic clocks on GPS satellites run slightly faster than clocks on Earth's surface because they're higher up where space-time is less curved. The GPS system corrects for this automatically. Every time you navigate with your phone, you're relying on Einstein's predictions being accurate. General relativity also predicts gravitational lensing. Light follows geodesics through curved space-time, just like everything else. So, if light passes near a massive object, its path will curve. A massive object can act like a lens, bending light that passes near it. First, observed in 1919 during a solar eclipse. Astronomers photographed stars near our star during the eclipse when the solar glare didn't overwhelm the starlight. They found that stars appeared slightly displaced from their known positions. The solar gravity was bending the starlight passing near it, making the stars appear in slightly different positions. The amount of displacement matched Einstein's predictions precisely. This observation made Einstein world famous overnight. Today, gravitational lensing is a standard tool in astronomy. When light from a distant galaxy passes near a massive object, like a galaxy cluster between us and that distant galaxy, the light gets bent. Sometimes, the light takes multiple paths around the massive object, and we see multiple images of the same distant galaxy. Or the galaxy gets stretched into arcs or rings. By studying these lensed images, astronomers can map the distribution of mass in the lensing object, including dark matter, which we can't see directly, but which still curves spacetime. Black holes are the most extreme example of curved spacetime. A black hole is a region where spacetime is so severely curved that nothing, not even light, can escape. The boundary of no return is called the event horizon. Once you cross it, all possible paths through spacetime lead inward toward the center. There's no way out. Not because something is pulling you in, but because space-time itself is curved so extremely that all geodesics point inward. Black holes form when massive stars collapse at the end of their lives. A star is a balance between gravity trying to compress it and pressure from nuclear fusion pushing outward. As long as the star is fusing hydrogen, helium, or heavier elements in its core, the pressure keeps the star from collapsing. Eventually, a massive star runs out of fuel, the fusion stops, the outward pressure disappears. Gravity wins. The star collapses. If the star is massive enough, more than roughly 20 times the mass of our own star, the collapse doesn't stop. The entire star compresses into an infinitely small point called a singularity. Around that singularity is the event horizon. The size of the event horizon depends on the mass. For a black hole with the mass of our star, the event horizon would be around 3 kilometers, or approximately 2 miles in radius. That's called the Schwarzschild radius. after Carl Schwarzschild, who calculated it in 1916, just months after Einstein published General Relativity. For a black hole with 10 solar masses, the radius would be roughly 30 kilometers or 19 miles. For a supermassive black hole with 1 billion solar masses, like the ones at the centers of galaxies, the radius would be nearly 3 billion kilometers or 1.9 billion miles. Larger than the orbit of Saturn, something that bends people's minds. From the perspective of someone falling into a black hole, they cross the event horizon in finite time. They'd fall through in seconds or minutes or hours, depending on the black hole's mass. But from the perspective of someone watching from outside, the falling person never quite reaches the event horizon. As the person approaches the horizon, time dilation becomes more and more extreme. Time passes slower and slower for the falling person relative to the outside observer. The light from the falling person becomes increasingly redshifted, shifting from visible light to infrared to radio waves, becoming dimmer and dimmer. Eventually, the person appears to freeze just outside the event horizon, fading from view. But this is just a perspective effect. The person experiences themselves falling through normally. Inside the event horizon, space-time is so warped that the future points toward the center. Just as surely as your future in normal space-time points forward in time, your future inside a black hole points toward the singularity. You can no more avoid hitting the singularity than you can avoid moving forward in time. The singularity isn't a place in space you can avoid by moving sideways. It's a moment in your future that you will inevitably reach. At the singularity, space-time curvature becomes infinite. Matter is compressed to infinite density. Our current theories break down. General relativity predicts the singularity, but can't describe what happens there because the math gives infinities, which usually means the theory has reached its limits. Most physicists think that quantum effects, which general relativity doesn't include, become important at some point before you reach the true singularity. But we don't have a complete theory of quantum gravity yet, so we can't say for sure what happens at the very center of a black hole. The singularity raises profound questions about the nature of space-time itself. Is infinite curvature physically real, or does it signal that our description fails? Some physicists think space-time itself might dissolve at the Planck scale approximately 10 to the minus 35 meters, replaced by something more fundamental, perhaps a quantum foam where space and time lose their classical meaning. The singularity might not be a point of infinite density, but rather a region where our concepts of space and time simply stop applying. There's also the cosmic censorship conjecture, proposed by Roger Penrose. It states that all singularities are hidden inside event horizons, invisible to outside observers. Nature seems to enforce this rule. We don't see naked singularities, singularities without event horizons. Why? If naked singularities existed, light from them could reach us. And we'd observe regions where physical laws break down, where predictability fails. The universe would have visible flaws in its causal structure. Cosmic censorship protects us from this, though we don't fully understand why nature enforces it. Some extreme scenarios, like colliding black holes or rapidly spinning black holes, might briefly create naked singularities before they're covered by event horizons. These scenarios are active areas of research, testing whether cosmic censorship always holds or has loopholes. There's a lot of misconception about black holes. People think they're like cosmic vacuum cleaners, sucking in everything around them. Not true. A black hole only pulls on things gravitationally, just like any other object with mass. If our star suddenly became a black hole with the same mass, which it won't because it's not massive enough, Earth's orbit wouldn't change. We'd still orbit at the same distance. We'd freeze because the star wouldn't be radiating light and heat anymore, but we wouldn't get sucked in. You only get into trouble with a black hole if you get very close, closer than you could get to a normal star, because the star's physical surface would be in the way. With a black hole, the physical matter has collapsed inside the event horizon, so you can get much closer to the center of mass. That's when the tidal forces become extreme. Tidal forces are differences in gravitational pull across an object. Earth's tides are caused by the moon pulling slightly harder on the side of Earth facing it than on the side facing away. With normal objects like Earth or the moon, tidal forces are gentle. But near a black hole, they become savage. If you fell feet first toward a black hole, your feet would be closer to the black hole than your head. The pull on your feet would be stronger than the pull on your head. The difference would stretch you. As you got closer, the stretching would become more and more extreme. Eventually, you'd be pulled apart, stretched like spaghetti. Physicists have a term for this: spaghettification, a real term used in technical papers. For a small black hole, spaghettification would happen before you even reached the event horizon. For a supermassive black hole, the event horizon is so far from the center that tidal forces at the horizon are relatively gentle. You could cross the event horizon without immediately being torn apart. You'd only get spaghettified much later as you fell closer to the singularity. Black holes aren't completely black. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon, now called Hawking radiation. The basic idea is that empty space isn't truly empty. Quantum mechanics tells us that particles and antiparticles are constantly popping into existence in pairs and then annihilating each other almost immediately. Normally doesn't lead to anything observable, but near a black hole's event horizon, one particle might fall into the black hole while the other escapes. From outside, it looks like the black hole is emitting radiation. This radiation carries energy away from the black hole, so the black hole gradually loses mass and shrinks over time. Black hole evaporation. The effect is incredibly slow for large black holes. A black hole with the mass of our star would take approximately 10 to the 67 years to evaporate. That's 10 with 67 zeros after it. For comparison, the universe is only roughly 13.8 billion years old. That's around 10 to the 10 years. So a solar mass black hole would take vastly longer than the current age of the universe to evaporate. For supermassive black holes, the evaporation time is even longer, far beyond any meaningful timescale. But for tiny black holes, if they exist, evaporation could be fast. A black hole with the mass of a mountain would evaporate in approximately 1 billion years. A black hole with the mass of a ship would explode in a fraction of a second, releasing energy equivalent to multiple nuclear bombs. Fortunately or unfortunately, depending on your perspective, we've never observed any primordial black holes of such small size, and we don't know if they exist. Gravitational waves are one of the most spectacular confirmations of general relativity. According to Einstein's theory, accelerating masses produce ripples in spacetime itself. These ripples travel outward at the speed of light, carrying energy away from their source. Imagine throwing a rock into a pond. Ripples spread out across the water's surface. Gravitational waves are similar, except they're ripples in the fabric of space-time itself. As a gravitational wave passes through a region of space, it alternately stretches and squeezes that space in perpendicular directions. Einstein predicted gravitational waves in 1916, but thought they'd be far too weak to ever detect. For decades, they remained purely theoretical. Then in the 1970s, Astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other. They observed that the orbit was gradually decaying. The two stars were slowly spiraling inward. The rate of decay matched exactly what you'd expect if the system was losing energy to gravitational waves. Indirect evidence that gravitational waves exist. Hulse and Taylor won the Nobel Prize for this discovery in 1993. But detecting gravitational waves directly required building incredibly sensitive instruments. In the United States, scientists built the Laser Interferometer Gravitational Wave Observatory, called LIGO. LIGO consists of two facilities, one in Louisiana and one in Washington State, separated by 3,000 kilometers or 1,900 miles. Each facility has two arms, 4 kilometers or 2.5 miles long, arranged in an L shape. Laser beams bounce back and forth along these arms. If a gravitational wave passes through, it stretches space in one direction and squeezes it in the perpendicular direction. The change in distance is incredibly small. When LIGO made its first detection, the change was roughly 1/10,000th the diameter of a proton. Like measuring the distance to the nearest star to within the width of a human hair. The precision required is almost incomprehensible. On September 14, 2015, both LIGO detectors picked up a signal. A gravitational wave had swept through Earth. By analyzing the signal, scientists determined it came from two black holes, 29 and 36 times the mass of our star, spiraling into each other 1.3 billion light-years away. As the black holes orbited each other, they emitted gravitational waves, losing energy and spiraling inward faster and faster. In the final fraction of a second, they merged, creating a single black hole 62 times the mass of our star. Wait a minute. 29 plus 36 equals 65, not 62. What happened to those three solar masses? They were converted entirely into gravitational wave energy according to Einstein's famous equation E equals mc squared. In a fraction of a second, this merger released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. The power output during that brief moment was roughly 50 times the power output of all the stars in the universe combined. Hard to wrap your mind around that. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most are black hole mergers, but some are neutron star mergers. In 2017, LIGO and Virgo detected gravitational waves from two neutron stars colliding. This event was also observed with traditional telescopes across the electromagnetic spectrum from gamma rays to radio waves. The first time an astronomical event was observed with both gravitational waves and light. This ushered in a new era of multi-messenger astronomy, where we study cosmic events using different kinds of signals. What makes gravitational wave astronomy revolutionary isn't just detecting these events, it's what we learn from them. When neutron stars merge, the gravitational wave signal encodes information about their internal structure. Neutron stars are laboratories for extreme physics, with matter compressed to densities where atomic nuclei merge into exotic states. Different theories about how matter behaves under these conditions, different equations of state, predict slightly different gravitational wave signatures during a merger. By analyzing the waves, we're essentially probing the interior structure of neutron stars, conducting experiments on matter at nuclear densities that we could never achieve on Earth. These observations also test fundamental physics. The speed of gravitational waves equals the speed of light to extraordinary precision. This wasn't guaranteed by theory. Some alternative theories of gravity predict different speeds. The LIGO-Virgo observations constrain or rule out entire classes of modified gravity theories. Every detection is simultaneously a discovery and a test, building confidence in general relativity while searching for any deviation that might point toward new physics. Gravitational waves also offer a unique way to measure cosmic distances. The amplitude of the wave tells us how far away the source is, while the frequency evolution tells us the masses of the merging objects. If we can also identify the host galaxy with traditional telescopes, we can measure both the distance and the galaxy's recession velocity. This gives us an independent measurement of the universe's expansion rate, potentially resolving current tensions between different measurement methods that give slightly different results. Gravitational wave cosmology might answer one of the most pressing questions in modern astronomy. Is the universe expanding faster or slower than our standard model predicts? Gravitational waves give us a completely new way to observe the universe. Light can be blocked by dust or gas, but gravitational waves pass through matter almost unimpeded. They carry information about events we could never see with traditional telescopes, like the insides of supernovas or the very early universe moments after the Big Bang. In the coming decades, even more sensitive gravitational wave detectors will be built. The Laser Interferometer Space Antenna, called LISA, will consist of 3 spacecraft arranged in a triangle with sides 5 million kilometers or 3 million miles long. It will detect lower frequency gravitational waves from sources like supermassive black holes merging at the centers of galaxies. Events LIGO can't detect because it's designed for higher frequencies. Dark matter and dark energy have puzzled scientists for decades. When astronomers study galaxies, they measure how fast stars orbit the galactic center. Based on visible matter, stars on the outer edges should move much slower than they do. The only explanation is additional mass we can't see providing extra gravitational pull. We call this dark matter. It doesn't emit light or any electromagnetic radiation. That's why it's dark. But it has mass, so it curves space-time and affects visible matter through gravity. Roughly 85% of the matter in the universe is dark matter. Only 15% is ordinary matter that makes up stars, planets, and people. What is dark matter? We don't know. It's not just dark clouds of normal matter like planets or dust, because such objects would absorb and block light from objects behind them. Dark matter doesn't do that. It's completely transparent. Leading theories suggest it's made of undiscovered subatomic particles that don't interact with light or normal matter except through gravity. Scientists are building detectors deep underground to try to catch dark matter particles colliding with normal atoms. So far, they haven't detected anything conclusive. The search continues. Dark energy is even more mysterious. In 1998, astronomers studying distant supernovas made a shocking discovery. The universe's expansion is accelerating, completely unexpected. After the Big Bang, the universe started expanding. Everyone assumed that gravity would gradually slow that expansion over time. The universe might eventually stop expanding and collapse back in a big crunch, or it might expand forever but at a decreasing rate. But acceleration? That suggested something was pushing the universe apart, counteracting gravity. This mysterious something is called dark energy. It appears to be a property of space itself. As the universe expands, creating more space, there's more dark energy. This drives faster expansion, which creates even more space and even more dark energy. A runaway process. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter is around 27%. Ordinary matter is approximately 5%. We live in a universe where 95% of it is stuff we don't understand. That should be humbling. The existence of dark energy has profound implications for the universe's fate. Because the expansion is accelerating, distant galaxies are moving away from us faster and faster. Eventually, they'll be moving away so fast that their light can no longer reach us. In the far future, trillions of years from now, the universe will be a much lonelier place. Most galaxies will be beyond our cosmic horizon. Only the galaxies in our local group, held together by gravity into a single structure, will remain visible. The rest of the universe will have expanded away beyond reach. Civilizations arising in that distant future would look out and see only their own galaxy and a handful of neighbors. They'd have no way to know the universe had ever been larger or fuller. Everything we've learned about cosmology, the Big Bang, the expansion of the universe, would be inaccessible to them. They'd be observationally cut off from understanding the history and structure of the cosmos. We're fortunate to exist at a time when we can still observe and study the broader universe. Cosmology is the study of the universe as a whole. General relativity describes not just gravity, but the structure and evolution of the entire universe. In 1922, Alexander Friedmann used Einstein's equations to show that the universe must be either expanding or contracting. It can't be static. Einstein initially resisted this, believing the universe was eternal and unchanging. Then, in 1929, Edwin Hubble observed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it's receding. Proved the universe is expanding. Space itself is stretching, carrying galaxies apart. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward far enough, and everything was compressed into an incredibly hot, dense state. The Big Bang. Not an explosion in space, but the expansion of space itself. Evidence is overwhelming. First, galaxies are moving apart. Second, the universe is filled with microwave radiation called the cosmic microwave background, the afterglow of the Big Bang from when the universe was only around 380,000 years old. Third, the abundances of light elements match predictions. In the first few minutes after the Big Bang, nuclear fusion created hydrogen, helium, and traces of lithium. The ratios we measure today match the predictions precisely. The Big Bang theory says the universe had a beginning roughly 13.8 billion years ago. Before that, there was no before in any meaningful sense, because time itself began with the Big Bang. Asking what came before the Big Bang is like asking what's north of the North Pole. A meaningless question. Time is part of the universe, part of space-time. When space-time began, time began. There was no earlier time. The first fractions of a second after the Big Bang are where things get speculative. At extremely high temperatures and densities, we need a theory of quantum gravity to describe what happens. We don't have one yet. String theory, loop, quantum gravity, and other approaches are being developed, but none are complete or confirmed. So we can't say with certainty what happened in the very first instant. But we can say with confidence what happened from around 1 second onward, because our theories work well in that regime and match observations perfectly. One question people often ask is whether the universe is infinite or finite. The answer is, we don't know. The observable universe is finite. It's the region of space from which light has had time to reach us since the Big Bang, approximately 93 billion light-years across. Beyond that is space we can't see because light from those regions hasn't reached us yet. But that doesn't mean the universe ends there. Space could extend far beyond what we can observe, perhaps infinitely. Current observations suggest the universe is spatially flat on the largest scales, which is consistent with it being infinite. But it could also be very large but finite, curved back on itself like the surface of a sphere is finite but has no edge. We don't have enough information to know for sure. Other predictions of general relativity deserve mention. One is frame dragging. A massive rotating object drags space-time around with it as it spins. The effect is incredibly small for objects like Earth, but it has been measured. In 2004, NASA launched Gravity Probe B, a satellite carrying 4 ultra-precise gyroscopes. These gyroscopes were so perfectly spherical that if you scaled them up to the size of Earth, the tallest mountains would be only around 2 meters or 6 feet high. The satellite orbited Earth for over a year, measuring tiny changes in the gyroscope's orientations caused by frame dragging. The results confirmed Einstein's predictions. Earth's rotation dragged space-time around with it, and the gyroscopes detected that drag. Frame dragging is much more significant near rapidly rotating black holes. A black hole can have 3 properties: mass, electric charge, and angular momentum, which means it's spinning. Most black holes probably have little to no charge, because charge tends to attract opposite charges and neutralize. But angular momentum is different. If a star is rotating when it collapses, and all stars rotate at least a little, the resulting black hole will be spinning. A spinning black hole drags space-time around it in a vortex. This creates an ergosphere, a region outside the event horizon where space-time is being dragged around so forcefully that nothing can remain stationary. You'd have to move along with the rotation. In principle, you could extract energy from a rotating black hole using a process called the Penrose process. You drop an object into the ergosphere. The object splits into 2 pieces. One piece falls into the black hole, carrying negative energy from the black hole's perspective. The other piece escapes with more energy than the original object had. The black hole loses angular momentum and slows down. You've extracted rotational energy from the black hole. Might sound like science fiction, but it's a legitimate consequence of general relativity. Whether any civilization could actually do this in practice is another question. Another fascinating prediction involves closed time-like curves, which are paths through space-time that loop back on themselves, allowing travel into the past. In certain solutions to Einstein's equations, like the Gödel metric and rotating wormholes, these paths exist. You could, in principle, travel along such a path and arrive at an earlier time. Raises all the problems with time travel, like paradoxes. If you went back in time and prevented your own birth, would you still exist to go back? General relativity doesn't forbid closed time-like curves, but most physicists think they're impossible for other reasons. Perhaps quantum mechanics prevents them. Perhaps the conditions needed to create them are physically unrealizable. Or perhaps they exist, but information or objects traveling through them would be destroyed by quantum effects. We don't know. An open question. General relativity has been tested in many ways over the past century, and it's passed every test with flying colors. But we know it's not the final theory. It's incompatible with quantum mechanics, our other fundamental theory. Quantum mechanics describes the microscopic world of atoms and particles. General relativity describes the macroscopic world of stars and galaxies. Both theories work brilliantly in their respective domains. But when you try to apply both to the same situation, like the interior of a black hole or the first instant of the Big Bang, they give contradictory answers. We need a unified theory of quantum gravity. String theory and loop quantum gravity are leading candidates, but neither is confirmed. Until we have a complete quantum theory of gravity, there will be aspects of the universe we can't fully understand. Despite this, general relativity remains one of the most successful theories in science. It has revolutionized our understanding of the cosmos. It predicted black holes, gravitational waves, the Big Bang, and much more, all of which have been confirmed. It's the foundation of modern cosmology, and it all comes from a simple but profound idea. Gravity isn't a force. It's the curvature of space-time. Consider your current experience. You're sitting or standing somewhere right now. You feel weight. If you're sitting, you feel the chair pushing up on you. If you're standing, you feel the floor beneath your feet. In Newtonian terms, this would be gravity pulling you down. But general relativity reveals something more subtle. The chair or floor exerts electromagnetic forces that resist your body's natural tendency to move along a particular path through space-time, a geodesic that would take you toward Earth's center. What you interpret as weight is actually the sensation of this resistance, not a downward pull. If the floor suddenly vanished and you started falling, you'd feel weightless. Not because gravity stopped, but because you're now free to follow your geodesic. Free fall. Your natural state of motion in space-time. Astronauts in orbit are weightless because they're in free fall, nothing pushing on them. They're experiencing their natural motion through space-time. From the perspective of space-time geometry, free fall is the natural state. Weight is the abnormal state caused by something pushing on you. We usually think of it the opposite way. We think sitting still is natural and falling requires an explanation. But from the viewpoint of general relativity, falling is natural and sitting still requires an explanation. That explanation is the electromagnetic forces from the floor or chair preventing you from following your geodesic. This might seem like word games, but it has real consequences. It changes how we think about motion and forces. In Newtonian physics, you need a force to change an object's motion. An object at rest stays at rest unless a force acts on it. An object in motion stays in motion in a straight line unless a force acts on it. Gravity is the force that makes things fall. But in general relativity, gravity isn't a force. An object in freefall is following the straightest possible path through curved space-time. No force is needed. Electromagnetic forces, the resistance of matter, change your motion by preventing you from falling. This perspective helps explain why all objects fall at the same rate in a vacuum, regardless of their mass. Galileo supposedly dropped 2 balls of different weights from the Leaning Tower of Pisa to demonstrate this. Whether he actually did that experiment is disputed, but the principle is true. In the absence of air resistance, a feather and a hammer fall at the same rate. The Apollo 15 astronauts demonstrated this on the moon, where there's no air. They dropped a feather and a hammer simultaneously, and both hit the ground at the same time. In Newtonian physics, this is a curious coincidence. The gravitational force on an object is proportional to its mass, but the acceleration produced by a force is inversely proportional to mass. The two effects exactly cancel, giving the same acceleration regardless of mass. Why? Newton couldn't explain it, just how nature worked. But in general relativity, it makes perfect sense. Objects aren't being pulled by a force proportional to their mass. They're following geodesics through space-time. The curvature doesn't care about an object's mass. All objects follow the same geodesics, so they all fall at the same rate. Natural and inevitable, not a curious coincidence. Why can't you feel gravity during free fall? In a small enough region of space-time, every part of your body follows essentially the same path through curved space-time. There are no differential forces stretching or compressing you. Gravity becomes locally undetectable. The equivalence principle in action. Quote, "You can't distinguish between floating in deep space and freely falling in a gravitational field from within your own reference frame. However, in a large enough region or for a long enough time, tidal forces become noticeable. These are caused by the curvature of space-time varying from place to place. Your feet might be following a geodesic that converges slightly with the geodesic your head is following. Over a large enough distance, this convergence becomes significant. That's a tidal force. For objects in orbit around Earth, tidal forces are tiny. The International Space Station is only around 400 kilometers or 250 miles from Earth's center, which is very close compared to Earth's radius of 6,400 kilometers or 4,000 miles. The curvature doesn't vary much over that short distance. But for an object falling into a black hole, tidal forces become enormous because space-time curvature changes rapidly with distance. Experimental tests confirmed general relativity. The first test was the deflection of starlight during the solar eclipse of 1919. According to Newton, light shouldn't be affected by gravity because light has no mass. But according to Einstein, light follows geodesics through curved space-time. Our star curves space-time, so light passing near it should have its path bent. Arthur Eddington led expeditions to observe the eclipse from two locations, Sobral in Brazil and Principe, an island off West Africa. The idea was to photograph stars near the solar disk during the eclipse and compare their positions to their known positions when our star wasn't nearby. If Einstein was right, stars should appear displaced because their light had been bent by solar gravity. The results showed displacement of approximately 1.8 arcseconds for light grazing the solar surface. Less than 1/2000th of a degree, but it was measurable and matched Einstein's predictions. This made front-page news worldwide. Einstein became a celebrity overnight. The New York Times headline read, "Lights all askew in the heavens. Men of science more or less agog." Since then, gravitational lensing has been observed countless times with far greater precision. Modern telescopes routinely see lensed images of distant galaxies, bent into multiple images or arcs by galaxy clusters in the foreground. We use gravitational lensing as a tool to map the distribution of mass, including dark matter, in those clusters. Another key test was the perihelion precession of Mercury mentioned earlier. When Einstein completed general relativity in 1915, one of the first things he did was calculate Mercury's orbit. General relativity predicts that space-time curvature near our star causes extra precession. When Einstein calculated the amount, he got exactly 43 arcseconds per century. The decades-old mystery was solved in an instant. Einstein later said, this was one of the happiest moments of his life. Gravitational redshift provides another crucial test. Light climbing out of a gravitational well loses energy. For light, energy is related to frequency. Lower energy means lower frequency and longer wavelength. For visible light, this shifts the color toward the red end of the spectrum. First, measured in 1960 using the Mossbauer effect, a technique that allows extremely precise measurements of frequency. Scientists put a radioactive source at the top of a tower and a detector at the bottom. The gamma rays emitted by the source were slightly redshifted by the time they reached the detector, exactly as general relativity predicted. Light from our star shows a small but measurable redshift compared to laboratory sources. From white dwarf stars, the redshift reaches approximately 50 parts per million. From neutron stars, light is redshifted by around 30%. Near a black hole's event horizon, photons climbing out lose so much energy that the redshift becomes enormous. Light, barely escaping the horizon, shifts to infinitely low frequencies. This redshift also appears cosmologically. As the universe expands, light traveling through space gets stretched, its wavelength increasing. By measuring how much distant galaxies' light has redshifted, we determine their distance and how long ago that light was emitted. Time dilation has also been measured using extremely accurate atomic clocks. In 2010, scientists at the National Institute of Standards and Technology showed they could detect time dilation over a height difference of just 33 centimeters, or roughly 1 foot. They placed 2 atomic clocks, one 33 centimeters higher than the other. The higher clock ticked slightly faster because it was in a slightly weaker gravitational field. The difference was only around 90 trillionths of a second per day, but it was measurable. Stunning precision. Shows that general relativity holds even for tiny differences in gravitational potential. The orbit decay of binary pulsars is another crucial test. A pulsar is a rapidly rotating neutron star that emits beams of radio waves from its magnetic poles. As the pulsar rotates, these beams sweep across space like a lighthouse beam. If one of these beams points toward Earth, we see regular pulses of radio waves. Some pulsars are in binary systems orbiting another neutron star, or a white dwarf. The Hulse-Taylor binary pulsar consists of 2 neutron stars orbiting each other every 7.75 hours. General relativity predicts that this system should emit gravitational waves. As it does, it loses energy. The orbit should shrink and the orbital period should decrease. Hulse and Taylor monitored the system for years and found that the orbital period was decreasing by exactly the amount predicted if the system was radiating gravitational waves. Over decades of observations, the agreement has been extraordinary. The orbit is decaying at precisely the predicted rate. This was the first indirect evidence that gravitational waves exist, decades before LIGO detected them directly. The direct detection of gravitational waves by LIGO is perhaps the most spectacular confirmation of general relativity. Not only did LIGO detect waves, but the waveform, the shape of the signal, matched predictions from computer simulations of black hole mergers. By analyzing the signal, scientists could determine the masses of the merging black holes, their spins, how far away the merger happened, and many other details. The match between observation and theory is remarkable. General relativity predicts not just that gravitational waves exist, but their exact properties and how they propagate through spacetime. The LIGO detections confirm all of this. General relativity has also been tested in strong field regimes near black holes. The Event Horizon Telescope, a global network of radio telescopes working together, took the first image of a black hole's shadow in 2019. The black hole is at the center of the galaxy M87, approximately 55 million light-years away. The image shows a dark central region, the black hole's shadow, surrounded by a bright ring of emission from hot gas orbiting the black hole. The size and shape of the shadow match predictions from general relativity. If gravity worked differently, the shadow would look different. In 2022, the Event Horizon Telescope imaged the black hole at the center of our own galaxy, Sagittarius A star. Again, the image matched predictions. These observations are testing general relativity in some of the most extreme conditions in the universe, near supermassive black holes where space-time is severely warped, and the theory still holds. You might wonder, if general relativity has passed every test, why do we think it might be wrong or incomplete? The reason is that it doesn't account for quantum mechanics. Quantum mechanics is the theory of the microscopic world. It describes how particles like electrons, photons, and quarks behave. Quantum mechanics is probabilistic. It deals with waves of probability. Particles don't have definite positions or velocities until you measure them. Before measurement, they exist in a superposition, a combination of many possible states. Measuring the particle collapses this superposition, and you get one specific outcome, completely alien to general relativity, which is deterministic. In general relativity, if you know the curvature of space-time and the positions and velocities of objects at one time, you can calculate their past and future trajectories with certainty. There's no probability, no uncertainty, no superpositions. The theories operate on different principles and don't fit together. For most situations, not a problem. Quantum mechanics handles the small stuff. General relativity handles the big stuff. They rarely need to work together. But in certain extreme situations, both are important. Inside a black hole, for instance, space-time curvature becomes infinite at the singularity. But at such small scales and high densities, quantum effects must be significant. We need a theory that combines quantum mechanics and general relativity to describe what happens. Similarly, at the very beginning of the Big Bang, the entire universe was smaller than an atom. Quantum effects were crucial, but so was the curvature of space-time. Again, we need a unified theory. String theory is one attempt to unify quantum mechanics and gravity. In string theory, particles aren't point-like. They're tiny, vibrating strings. Different vibration patterns correspond to different particles. Electrons, photons, quarks, all are different vibrations of the same fundamental strings. Gravity emerges naturally in string theory. The graviton, the hypothetical particle that carries the gravitational force, is one of the vibration patterns. String theory requires extra dimensions of space beyond the 3 we experience. Current versions suggest 10 or 11 total dimensions. The extra dimensions are supposedly curled up so small we don't notice them. But this is speculative. String theory makes few testable predictions, and so far none have been confirmed or falsified. Mathematically elegant, but it's not clear if it describes the real world. Loop quantum gravity takes a different approach. It tries to quantize space-time itself, treating it not as a smooth continuum, but as a network of tiny loops. Space and time would be discrete at the smallest scales, coming in indivisible chunks. This would prevent the infinities that plague our current theories. But loop quantum gravity also struggles to make testable predictions. There are other approaches too. Theories involving higher dimensions. Theories where gravity is an emergent phenomenon arising from something more fundamental. Even theories questioning whether space-time is fundamental at all. The truth is, we don't know. Quantum gravity is one of the biggest unsolved problems in physics. Until we solve it, our understanding of the universe will be incomplete. We won't fully understand the Big Bang, the insides of black holes, or the ultimate fate of information that falls into a black hole. Some of the deepest mysteries in science. What does general relativity mean for you, personally? For most people, most of the time, the effects are too small to notice. Navigation relies on general relativity, but you don't think about that when you use your phone. The time dilation you experience standing up versus sitting down is roughly 10 trillionths of a second per day. You'll never notice. So why does it matter? It matters because understanding general relativity changes how you see reality. You live in a universe where space and time are unified into space-time. Space-time is flexible, curved by mass and energy. You're not held to Earth by an invisible force pulling you down. You're following the natural contours of curved space-time. Every object in the universe, from a grain of sand to a galaxy cluster, curves space-time around it. These curvatures interact in complex ways, creating the rich tapestry of motion we observe. Planets orbiting stars, stars orbiting galactic centers, galaxies clustering together. All of it is objects following geodesics through a dynamically curving, four-dimensional space-time. When you look up at the night sky, you're seeing objects separated by vast distances, but you're also seeing the past. Light takes time to travel. The light from our star is 8 minutes old when it reaches you. Light from the nearest star is over 4 years old. Light from distant galaxies is billions of years old. You're literally looking back in time. The universe has a history written in light, and that light has been traveling through curved space-time to reach your eyes. You're also part of this cosmic story. The atoms in your body were forged in stars billions of years ago. Those stars exploded as supernovas, scattering their atoms into space. Over eons, those atoms drifted, eventually coming together in a cloud of gas that collapsed under its own gravity to form our solar system. Earth formed from that material, and eventually, after billions of years of evolution, those atoms arranged themselves into you. You're made of stardust. Not a metaphor, literally true. The carbon in your cells, the iron in your blood, the calcium in your bones, all were created in stellar furnaces and supernova explosions and have been traveling through the cosmos for billions of years before ending up in you. General relativity tells us that space-time itself is dynamic, not a static stage on which events unfold. An active participant. It curves in response to mass and energy. Those curves affect how matter moves. And that moving matter curves space-time in turn. A feedback loop. This dynamic interplay between matter and space-time gives rise to all the gravitational phenomena we observe, from falling apples to black hole mergers to the expansion of the universe itself. There's a deep philosophical implication too. In Newton's view, space and time were absolute. They existed independently of the matter and events within them. They provided a fixed framework for the universe, but Einstein showed this isn't true. Space-time is relational. It's defined by the events and objects within it. Take away all the matter and energy, and it's not clear that space-time would even exist in a meaningful sense. The universe is not a container with stuff inside it. The universe is the stuff and the relationships between the stuff. Space-time is those relationships. This might sound abstract, but it has consequences. The universe is self-contained. There's no outside. The question, what's outside the universe, doesn't make sense because outside implies a spatial relationship and space is part of the universe. Similarly, what happened before the Big Bang? Doesn't make sense if time began with the Big Bang. These are questions that feel like they should have answers, but they're based on concepts that don't apply at the most fundamental level. Some people find this unsettling. The universe doesn't have an external explanation. It is the explanation. Others find it liberating. The universe is comprehensible on its own terms. We don't need to invoke anything outside it to understand how it works. The laws of physics, the properties of space-time, the constants of nature, these are the foundations, and everything builds from there. Where is gravitational physics headed? One exciting area is testing general relativity in even more extreme conditions. The Event Horizon Telescope is continuing to observe black holes, looking for any deviations from predictions that might hint at new physics. Future observations will track matter spiraling into black holes in real time, watching how space-time curvature affects the trajectories and emissions of doomed gas clouds. Scientists are particularly interested in measuring the photon ring, a bright, narrow band of light that orbits just outside the event horizon, completing multiple circuits before escaping to our telescopes. The exact structure of this ring encodes information about the black hole's spin and properties in ways that will test general relativity with unprecedented precision. Gravitational wave detectors are becoming more sensitive. LIGO is being upgraded. New detectors are being built in Japan and India. And LISA, the space-based detector, is planned for the 2030s. These will observe gravitational waves from a wider range of sources, giving us more opportunities to test general relativity and explore phenomena we can't study any other way. LISA's sensitivity to low-frequency waves will reveal supermassive black hole mergers occurring when distant galaxies collide. Events that happen too slowly for ground-based detectors, but that release staggering amounts of energy. Each detection adds another data point, confirming Einstein's equations work even in the most violent events the universe produces. Beyond confirmation, gravitational waves offer unique scientific opportunities. They let us study neutron star interiors, regions so dense that atomic nuclei merge into exotic matter states we can't reproduce in laboratories. When two neutron stars spiral together and merge, the gravitational wave signal encodes information about how matter behaves at nuclear densities and beyond. Different equations of state, the relationships between pressure, density, and temperature in ultra-dense matter, produce subtly different waveforms. By analyzing these signals, we're essentially conducting experiments on matter compressed far beyond anything achievable on Earth. Another frontier is the quest for quantum gravity. Several experiments are being designed to probe the interface between quantum mechanics and gravity. These are incredibly challenging because quantum gravitational effects are expected to be significant only at the Planck scale, approximately 10 to the minus 35 meters, 20 orders of magnitude smaller than a proton. We can't build particle accelerators that reach those energies. But there might be subtle effects we can measure indirectly. For instance, if space-time is discrete at the Planck scale, that might affect the propagation of light over cosmic distances in ways we could detect with sensitive enough instruments. Photons of different energies might travel at slightly different speeds through quantized space-time, arriving at Earth at slightly different times after journeying billions of light-years. No such effect has been detected yet, which constrains theories of quantum gravity. Some proposed theories predicted effects large enough that we should have seen them by now. Their absence rules out entire classes of quantum gravity models. There are also experiments testing whether gravity affects quantum superpositions. In quantum mechanics, objects can exist in superpositions of multiple states simultaneously until measured. But what happens when the objects are massive enough that their gravitational fields become significant? Does space-time itself become entangled with quantum states? Can you have a superposition of different space-time geometries? These questions probe the boundary between quantum mechanics and general relativity. Experiments with increasingly massive objects in quantum superpositions, perhaps molecules, or even tiny mirrors, might reveal where quantum behavior breaks down and classical space-time emerges, potentially pointing toward the correct theory of quantum gravity. Astronomers are also using gravity as a tool in increasingly sophisticated ways. Gravitational lensing can magnify distant objects, allowing us to see galaxies and stars that would otherwise be too faint. By studying how gravity bends light, we can map the distribution of dark matter in galaxy clusters. We can even use lensing to detect exoplanets, planets orbiting other stars, when the planet's gravity focuses light from a background star toward us in a brief, brightening event. More dramatically, gravitational lensing sometimes creates Einstein crosses, or Einstein rings, patterns where we see multiple images of a single distant quasar arranged around a foreground galaxy. The foreground galaxy's mass curves space-time so much that light from the background quasar takes multiple paths around it, each path arriving at Earth from a slightly different direction. By measuring the time delays between these multiple images, how long light takes to travel each path, astronomers can determine the expansion rate of the universe with impressive accuracy. Different paths through curved space-time have different lengths, so light traveling them arrives at different times. This technique provides an independent measurement of cosmic expansion that doesn't rely on traditional distance ladder methods, helping resolve ongoing debates about whether the universe is expanding faster or slower than our models predict. There's also the tantalizing possibility of detecting primordial gravitational waves, ripples in spacetime produced in the first moments after the Big Bang. These waves would carry information about the universe when it was far younger and smaller than anything we can currently observe. Detecting them would be a monumental achievement, opening a window into the earliest moments of cosmic history. Current experiments search for these primordial waves by looking at the cosmic microwave background, the afterglow of the Big Bang. Gravitational waves passing through space in the early universe would have left a distinctive pattern in the polarization of this ancient light, a swirling pattern called B-modes that would be the smoking gun signature of inflation, the hypothesized period of exponential expansion that occurred in the first fraction of a second after the Big Bang. The stakes are enormous. Detecting primordial gravitational waves would confirm inflation occurred, tell us about the energy scale at which it happened, and potentially reveal physics operating at energies 1 trillion times higher than anything we can achieve in particle accelerators. It would be like having a telescope that sees back to when the universe was only a tiny fraction of a second old, revealing conditions closer to the Big Bang than any other observation method can access. Beyond pure science, understanding gravity has practical, technological implications. GPS is the most obvious example, but there are others. Gravitational wave detectors require developing laser systems, vibration isolation, and measurement techniques of extraordinary precision. These technologies spin off into other fields. The same laser stabilization methods now help atomic clocks, ultra-sensitive measurements of material properties, and fundamental physics experiments. The mirror coatings developed for gravitational wave detectors, which must reflect light with minimal losses, find applications in telecommunications and optical instruments. Looking further ahead, some physicists speculate about manipulating space-time curvature for propulsion. If we could generate strong gravitational fields artificially, perhaps spacecraft could surf waves in space-time or create localized distortions that effectively move space around the ship rather than moving the ship through space. The Alcubierre drive is the most famous such proposal. Contract space in front of your ship and expand it behind, effectively moving faster than light without actually accelerating through space. Unfortunately, such schemes require exotic matter with negative energy density, something that may not exist or may be impossible to produce in sufficient quantities. Still, the fact that general relativity's equations permit such solutions, even if nature doesn't provide the ingredients, shows how profoundly different this theory is from Newtonian gravity. More plausibly, understanding gravity deeply might help with long-term space exploration challenges. Rotating space habitats use centrifugal acceleration to simulate gravity, an application of the equivalence principle. Future habitats might use more sophisticated arrangements, perhaps varying rotation rates to create different effective gravity levels for different purposes. Generating artificial gravity becomes crucial for long-duration missions where bone loss and muscle atrophy in zero gravity pose serious health risks. General relativity has fundamentally reshaped our understanding of the universe, not just a better version of Newton's theory, a completely different way of thinking about space, time, matter, and gravity. And it's been confirmed by every experiment and observation to date. One of the great intellectual achievements of humanity. One person, Albert Einstein, sitting and thinking, working out the implications of a few simple ideas, constructed a theory that describes the cosmos from the smallest scales we can probe to the largest structures we can observe. Remarkable. But the story doesn't end here. We know general relativity is incomplete. We're still searching for a deeper understanding that unifies it with quantum mechanics. We don't understand dark matter or dark energy, which make up 95% of the universe. We don't know whether the universe is finite or infinite, whether it will expand forever or eventually contract, whether there are other universes beyond our own. These are open questions. The universe still holds mysteries. And that's exciting. There's more to discover. Future scientists will look back on our time the way we look back on Newton's era. They'll appreciate what we got right, but they'll also see our blind spots, the questions we couldn't answer, the leaps we couldn't make. Science is a process of continual refinement. Each generation builds on the work of the last, getting closer to a true understanding of reality. We're part of that journey. What should you take away from all this? First, gravity isn't a force in the way you've been taught. Rather, it's the curvature of space-time. Objects follow geodesics through that curved space-time. When you feel weight, you're feeling electromagnetic forces preventing you from following your natural geodesic. In free fall, you're weightless because you're finally free to move along that natural path. Second, space and time are not separate. They're unified into space-time. And space-time is dynamic, curving in response to mass and energy. This curvature affects how objects move, which in turn affects the curvature. A beautiful interplay that gives rise to all gravitational phenomena, from planetary orbits to galaxy formation to the expansion of the universe itself. Third, general relativity has been confirmed by countless experiments and observations, from the precession of Mercury to the detection of gravitational waves to images of black hole shadows. Every test has supported Einstein's theory. The GPS in your phone corrects for relativistic time dilation. Gravitational lensing reveals dark matter distributions in galaxy clusters. Gravitational wave detections opened an entirely new window on the universe, one of the most successful scientific theories ever developed. Fourth, despite its success, general relativity is incomplete. It doesn't incorporate quantum mechanics. We need a theory of quantum gravity to fully understand the universe at its most fundamental level, inside black holes, at the moment of the Big Bang, at the Planck scale, where space-time itself might be quantized. That theory hasn't been found yet. It's one of the great challenges facing physics today, with string theory, loop quantum gravity, and other approaches competing to unify our understanding. Fifth, these ideas have practical applications beyond GPS. Gravitational lensing is a tool for astronomy, magnifying distant objects and mapping dark matter. Gravitational waves are a new way to observe the universe, revealing events invisible to traditional telescopes. Understanding gravity helps us understand everything from star formation to planetary systems to the large-scale structure of the cosmos. The precision measurement techniques developed for gravitational wave detectors spin off into other technologies. The atomic clocks that test time dilation enabled better navigation, timekeeping, and fundamental physics experiments. And finally, there's something profound about understanding that you live in a universe of curved space-time. Not just an abstract mathematical concept, the fabric of reality. Every moment of your life, you're moving through space-time, following geodesics, experiencing time dilation relative to other observers, interacting with the curvature created by Earth and our star and the galaxy, and all the mass energy in the universe. You're part of a vast cosmic dance that's been going on for 13.8 billion years and will continue for trillions more, humbling and awe-inspiring. When you drop a ball and watch it fall, you're not seeing a force pulling it down. You're seeing it follow the natural geometry of space-time. When you look up at the moon, you're seeing an object in free fall, endlessly circling Earth because that's the geodesic it follows through curved space-time. The universe operates according to these principles whether you understand them or not. But understanding them gives you a deeper appreciation for the reality you inhabit. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We're tiny creatures on a small planet, yet we've figured out the fundamental laws governing cosmic-scale phenomena. We've measured the curvature of space-time. We've detected ripples in that space-time from black holes colliding a billion light-years away. We've imaged the shadows of black holes at the centers of galaxies. We've traced the history of the universe back to fractions of a second after the Big Bang. Extraordinary. Suggests that the universe is fundamentally knowable. The laws of physics are the same everywhere. We can figure them out through careful observation, experimentation, and reasoning. That should give you hope. We're not helpless in the face of cosmic mysteries. We can understand, we have understood, and we'll continue to understand more. So the next time you think about gravity, don't think of it as a mysterious force pulling things down. Think of it as the shape of space-time. Think of yourself as moving through a four-dimensional geometry, following the contours of that geometry, experiencing its curvature. You're not standing still on a flat Earth with gravity pulling you down. You're accelerating upward through curved space-time, held in place by the electromagnetic forces from the ground. The ground is pushing you up constantly, preventing you from following your natural geodesic, which would take you toward Earth's center. That's weight. That's what you feel right now. And out there in space, planets are following their geodesics around stars. Stars are following their geodesics around galactic centers. Galaxies are following geodesics through the larger scale curvature of cosmic space-time. Light from distant galaxies has been traveling for billions of years through expanding space-time, carrying information about the ancient universe. Gravitational waves from cataclysmic events ripple through space-time at the speed of light, stretching and squeezing space as they pass. Black holes sit in regions where space-time curvature becomes so extreme that not even light can escape. All of this is described by Einstein's equations. All of it follows from the idea that gravity is geometry. It's been over a century since Einstein published general relativity. In that time, it's been tested in countless ways. It's made predictions that seemed absurd, but turned out to be true. It's survived every challenge. And it's given us a picture of the universe that's richer and stranger than anyone imagined. We live in a universe of curved space-time, where black holes lurk in the centers of galaxies, where gravitational waves ripple across cosmic distances, where time passes at different rates depending on where you are, where the history of the cosmos is written in the light reaching us from distant sources. The universe, as revealed by general relativity, beautiful, profound, and real. If you've made it this far, thank you for joining me on this journey through the nature of gravity and space-time. Understanding these concepts doesn't change your daily life in obvious ways. You'll still experience weight the same way. You'll still see objects fall, but you'll know what's really happening. You'll have a deeper understanding of the reality beneath the surface. And that's valuable in itself. Knowledge is its own reward. Understanding is its own justification. If you found this exploration worthwhile, a like or subscribe would help this channel continue making content like this. These deep dives take a lot of research and thought to put together. Your support makes it possible. And if you have questions or thoughts, leave them in the comments. I read them, and they often inspire future topics. Specific examples of how gravity shapes the universe at different scales will help make the abstract concepts more concrete. We'll start small and work our way up to the largest structures in the cosmos. At Earth's scale, gravity shapes everything from atmosphere to interior. The atmosphere exists because gravity holds it in place. Mars, being smaller with weaker gravity, lost most of its atmosphere over billions of years. The pressure at Earth's center reaches approximately 360 gigapascals, 3.6 million times atmospheric pressure, due to overlying rock. When Earth was molten early in its history, gravity sorted materials by density. The densest materials, mostly iron and nickel, sank to form the core, while lighter materials rose to form mantle and crust. The movement of liquid iron in the outer core generates Earth's magnetic field, which protects us from solar wind and cosmic radiation. Gravity also drives plate tectonics through mantle convection. Though solid rock, Earth's mantle flows like thick fluid over geological timescales. Heat from radioactive decay makes material rise, cool, and sink. This convection drags the crust around, creating plate motion. Mountains form where plates collide. Ocean trenches form where one plate subducts under another. All this activity is ultimately powered by gravity, acting on materials of different densities. At the solar system scale, our star's gravity dominates, it contains 99.86% of the system's mass. Planets follow elliptical orbits. Kepler's first law discovered in the early 1600s. Newton explained why with his law of gravitation. Einstein explained the mechanism. Our star curves space-time, and planets follow geodesics through that curved space-time. The planets themselves curve space-time too. Earth's gravity holds the moon in orbit. Jupiter's gravity dominates a huge region with at least 95 moons and profoundly affects the asteroid belt. There are gaps in the belt, called Kirkwood gaps, where almost no asteroids exist. These gaps correspond to orbital distances where asteroids would have periods that are simple fractions of Jupiter's period, 1/3, 1/2. Asteroids in those locations experience repeated gravitational tugs from Jupiter at the same point in their orbit. Over time, these periodic tugs push asteroids into different orbits, clearing the gaps through orbital resonance. Saturn's rings show similar effects. The rings contain countless particles of ice and rock, from dust grains to boulders, orbiting in a thin disk. But the rings have structure and gaps. The most prominent is the Cassini division, a dark gap between the A ring and B ring. This gap exists because particles orbiting there would resonate with Saturn's moon, Mimas. The repeated gravitational perturbations clear particles from that region. Other small moons shepherd the rings, keeping particles confined, a beautiful demonstration of gravity sculpting order from chaos. Comets from the distant Oort cloud occasionally fall toward the inner solar system. The Oort cloud is a spherical shell of trillions of comets surrounding the solar system out to roughly 1 light year. Sometimes a passing star or the galaxy's gravitational tide disturbs a comet's orbit, sending it falling sunward. As they approach our star, solar heating creates glowing tails. Sometimes they collide with planets. In 1994, comet shoemaker Levy 9 broke apart and slammed into Jupiter over several days. Astronomers worldwide watched as fragments slammed into Jupiter's atmosphere one by one, each impact releasing energy equivalent to millions of nuclear bombs, leaving dark scars visible for months. Gravity orchestrated everything. The comet wandered too close, tidal forces ripped it apart, then Jupiter's gravity pulled the fragments in. At stellar scales, gravity creates and destroys. Stars form when dense regions in giant molecular clouds collapse under their own gravity. These clouds are vast, hundreds of light years across, yet gravity acts on every particle. If a region is slightly denser, it pulls nearby material, becoming denser still, accelerating the collapse. As material falls inward, gravitational potential energy converts to heat. The center grows hotter and denser. Eventually, the core reaches millions of degrees and hydrogen fusion ignites. The energy released creates outward pressure that balances inward gravitational pull, hydrostatic equilibrium. The star shines steadily for billions of years. Our star is approximately 4.6 billion years old, halfway through its 10 billion year main sequence lifetime. Eventually, hydrogen fuel runs out. Fusion stops. Gravity wins temporarily. The core contracts and heats until helium fusion ignites, transforming the star into a red giant. When our star reaches this phase in roughly 5 billion years, it will expand past Earth's current orbit. For massive stars, the process continues through multiple fusion stages: helium to carbon, carbon to neon, oxygen to silicon, silicon to iron. Each stage releases less energy and lasts shorter than the previous. Iron fusion absorbs energy rather than releasing it. Once the core is iron, fusion stops. Nothing resists gravity. The core collapses in a fraction of a second. Electrons are crushed into protons, forming neutrons. The collapse rebounds, sending a shockwave that blasts outer layers into space in a supernova explosion. For weeks, the supernova outshines entire galaxies. The explosion scatters heavy elements into space. These elements seed new stars and planets. Every element heavier than helium in your body came from stellar fusion and supernova explosions. You're made of stellar ash. Gravity made those stars, crushed their cores, triggered the explosions, then brought the scattered material together to form new stars and planets, including Earth. Neutron stars are among the most extreme objects imaginable. Roughly 1.4 solar masses compressed into a sphere only 20 kilometers across. Density approximately 400 trillion times that of water to a teaspoon, would weigh 1 billion tons. Surface gravity is 200 billion times Earth's. If you could somehow stand there, which you couldn't because you'd be instantly crushed into a layer only atoms thick, you'd weigh billions of times more than on Earth. Light from the surface is gravitationally redshifted by 30%. Some neutron stars spin hundreds of times per second, emitting radiation beams from their magnetic poles. As they rotate, these beams sweep like lighthouse beams. If aimed at Earth, we see regular pulses, pulsars, nature's most precise timepieces. The regularity is so extreme that when pulsars were first discovered in 1967, some scientists briefly wondered if they might be signals from alien civilizations. The natural explanation, rapidly rotating neutron stars, turned out correct. For the most massive stars, even a neutron star can't resist gravity. If the core is massive enough, more than approximately 3 solar masses, gravity crushes the neutron star. Nothing can stop the collapse. The star becomes a black hole. All the mass compresses into a singularity. Around it forms the event horizon. Inside the horizon, space-time is so warped that all paths lead inward. Nothing escapes. Black holes come in different sizes. Stellar mass black holes form from supernova. They range from roughly 3 solar masses to maybe 50 or 100 solar masses. Then there are supermassive black holes at the centers of galaxies. These range from millions to billions of solar masses. How they formed is still debated. They might have grown by accreting matter and merging with other black holes over billions of years. Or they might have formed directly from the collapse of massive gas clouds in the early universe. Either way, gravity was the driving force. At the center of our galaxy is a supermassive black hole called Sagittarius A star. It has a mass of approximately 4 million solar masses. Astronomers have tracked stars orbiting this black hole. Some of these stars have orbital periods of just a few years. One star, called S2, orbits so close that it reaches speeds of around 2% of the speed of light at its closest approach. By watching these stars, astronomers have confirmed that there's a massive dark object at the galactic center that can only be a black hole. The Event Horizon Telescope imaged the glowing gas around Sagittarius A star, revealing the black hole's shadow. The observations match predictions from general relativity. Supermassive black holes affect their entire galaxies. The gravitational influence extends far beyond the event horizon. Stars orbit the galactic center. For the same reason planets orbit our star. They're following geodesics through space-time, curved by the central mass. The Milky Way is a spiral galaxy, approximately 100,000 light-years across, containing 200 to 400 billion stars. All these stars orbit the galactic center. Our star is roughly 26,000 light-years from the center. At this distance, it takes around 225 million years to complete one orbit. The last time our star was at its current position in its orbit, dinosaurs were just beginning to evolve on Earth. Galaxies themselves are held together by gravity, not solid objects, but billions of stars gravitationally bound. When galaxies pass close, their mutual gravity distorts them. Arms stretch. Stars stream into space. Sometimes galaxies merge, their central black holes eventually spiraling together. The Milky Way is currently absorbing the Sagittarius dwarf elliptical galaxy, tearing it apart and scattering its stars into long streams looping around our galaxy. At the center of our galaxy is a supermassive black hole called Sagittarius A star. It has a mass of approximately 4 million solar masses. Astronomers have tracked stars orbiting this black hole. Some of these stars have orbital periods of just a few years. One star, called S2, orbits so close that it reaches speeds of around 2% of the speed of light at its closest approach. By watching these stars, astronomers have confirmed that there's a massive dark object at the galactic center that can only be a black hole. The Event Horizon Telescope imaged the glowing gas around Sagittarius A star, revealing the black hole's shadow. The observations match predictions from general relativity. Supermassive black holes affect their entire galaxies. The gravitational influence extends far beyond the event horizon. Stars orbit the galactic center. For the same reason planets orbit our star. They're following geodesics through space-time, curved by the central mass. The Milky Way is a spiral galaxy, approximately 100,000 light-years across, containing 200 to 400 billion stars. All these stars orbit the galactic center. Our star is roughly 26,000 light-years from the center. At this distance, it takes around 225 million years to complete one orbit. The last time our star was at its current position in its orbit, dinosaurs were just beginning to evolve on Earth. Galaxies themselves are held together by gravity, not solid objects, but billions of stars gravitationally bound. When galaxies pass close, their mutual gravity distorts them. Arms stretch. Stars stream into space. Sometimes galaxies merge, their central black holes eventually spiraling together. The Milky Way is currently absorbing the Sagittarius dwarf elliptical galaxy, tearing it apart and scattering its stars into long streams looping around our galaxy. In approximately 4 billion years, we'll collide with Andromeda Galaxy, heading toward us at 110 kilometers per second. The collision will unfold over hundreds of millions of years. Individual stars likely won't collide. Space between them is too vast, but gas clouds will compress, triggering bursts of star formation. The night sky will be spectacular, with newborn stars and distorted galactic structures. Eventually, the two galaxies will merge into a single elliptical galaxy with a central black hole containing tens of millions of solar masses. Galaxy collisions are common throughout the universe. Gravity brings galaxies together. The universe is full of interacting, merging galaxies, pulling streams of gas and stars from each other. This is how galaxies grow. Small galaxies merge into larger ones, a process ongoing since the first galaxies formed 13 billion years ago. Galaxies aren't randomly distributed. They form groups and clusters. Our Milky Way belongs to the local group of roughly 80 galaxies, mostly small dwarfs, spanning about 10 million light-years. The total mass is around 2 trillion solar masses, mostly dark matter. The Virgo cluster, 54 million light-years away, contains about 1,500 galaxies with total mass around 1.2 quadrillion solar masses. Our local group is being pulled toward Virgo. We're part of the larger Virgo supercluster. Superclusters, hundreds of millions of light-years across, are among the universe's largest structures. On the grandest scales, the universe shows a cosmic web pattern. Galaxies arrange in filaments, long, thin structures stretching across space with voids between. Filaments intersect at nodes, where galaxy clusters form. This structure grew from tiny density variations in the early universe. Slightly denser regions had slightly stronger gravity, pulling in more matter, becoming denser, pulling in even more. Over billions of years, gravity amplified small differences into the grand architecture visible in galaxy surveys, mapping millions of objects. Gravitational time dilation is one of the strangest aspects of gravity. Real, measured, and has practical consequences every day. Time passes at different rates depending on the strength of the gravitational field you're in. The stronger the field, the slower time passes relative to someone in a weaker field. Not science fiction or metaphor, measured fact confirmed by countless experiments. Picture 2 identical atomic clocks, the most accurate timekeepers ever built. You put one on the ground and carry the other up a mountain. The clock on the mountain is higher up, farther from Earth's center, in a slightly weaker gravitational field. It runs slightly faster than the clock on the ground. When you bring them back together, they show different times. The difference is tiny, approximately a millionth of a second per day for typical mountains. But it's measurable with sufficiently accurate clocks, and it's real. The time dilation formula comes straight from the geometry of curved spacetime. The closer you are to a massive object, the more spacetime is curved, the slower time passes. For Earth, the effect is small because Earth isn't very massive, and its gravity is relatively weak by cosmic standards. But near neutron stars, time passes approximately 30% slower than far from the star. Near a black hole's event horizon, time dilation becomes infinite, time effectively stops from an outside observer's perspective, though someone falling in experiences nothing unusual at that boundary. These extreme effects lead to fascinating paradoxes about what different observers see when something approaches or crosses an event horizon. This has led to what's called the black hole information paradox. According to general relativity, information that falls into a black hole is lost. It can't escape. But, according to quantum mechanics, information can't be destroyed. It can be scrambled, but it must be preserved in some form. Creates a contradiction. What happens to information that falls into a black hole? Does it violate quantum mechanics? Or does general relativity need modification? The paradox runs deeper than it first appears. In quantum mechanics, the evolution of any system is reversible in principle. Given complete information about a system's quantum state at one time, you can calculate its state at any other time, forward or backward. But if information falls into a black hole and disappears, that reversibility is violated. The universe develops amnesia about what fell in. This violates unitarity, a fundamental principle of quantum mechanics. Stephen Hawking originally argued that information is genuinely lost, that black holes are the one place where quantum mechanics breaks down. This created an uproar in the physics community. For decades, theorists battled over the paradox. In the early 2000s, Hawking conceded he was wrong, proposing that information might be encoded in subtle correlations in the Hawking radiation emitted by black holes. But how exactly this works mathematically remains unclear. Recent work suggests the information might be encoded at the event horizon itself in a holographic manner. The holographic principle proposes that all the information about a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a hologram. For a black hole, the horizon acts as this boundary. Information about everything that fell in might be preserved in the horizon's structure, gradually released as the black hole evaporates through Hawking radiation. This would preserve unitarity, but requires quantum gravity to fully understand. The information paradox remains one of the deepest puzzles connecting quantum mechanics, gravity, and the nature of information itself. Another consequence of general relativity is that nothing can travel faster than light. Not because light has some special speed, rather, light travels along null geodesics, the boundary between time-like geodesics that objects with mass follow, and space-like paths that would require traveling backward in time. The speed of light is the speed of causality, the speed at which information can propagate through spacetime. Anything with mass must travel slower than light. As you accelerate an object approaching light speed, the energy required to accelerate it further increases without limit. To actually reach light speed would require infinite energy, which is impossible. Profound implications for space travel and communication. The distances between stars are measured in light years. Even traveling at close to light speed, it would take years to reach nearby stars. And due to time dilation, the faster you go, the less time you experience for the journey. If you could travel at 99% of light speed to a star 10 light years away, the trip would take just over 10 years from Earth's perspective, but you'd age only roughly 1.5 years due to time dilation. When you returned, you'd have aged 3 years, but more than 20 years would have passed on Earth. Everyone you knew would be older. Some might have died. You'd have traveled into their future, sometimes called the twin paradox. One twin stays on Earth, the other travels to a distant star at high speed and returns. When they reunite, the traveling twin is younger. Not a true paradox, because the situations aren't symmetric. The traveling twin accelerated and decelerated, experiencing forces that the Earth-bound twin didn't. Acceleration breaks the symmetry. The mathematics of special and general relativity predict exactly how much each twin ages, and the predictions have been confirmed by experiments with particles and atomic clocks. The numbers become dramatic at extreme speeds. Imagine traveling to a star 10 light-years away at 99% of light speed. From Earth's reference frame, the journey takes just over 10 years each way, about 20 years round trip. But due to time dilation, the traveler experiences only about 2.8 years of time passing during the journey. They age less than 3 years, while Earth ages 20. Return home and you're 17 years younger than your twin who stayed behind. Your children would be older than you remember. The world would have moved on without you. Push it further. At 99.9% of light speed, time dilation becomes even more extreme. A journey across the galaxy, 100,000 light-years, as measured by observers at rest, would take roughly 100,000 years from Earth's perspective. But the traveler would experience only about 4,400 years passing. Still longer than human lifetimes, but vastly compressed compared to the external universe. This isn't science fiction speculation. The mathematics is straightforward, confirmed every day in particle accelerators, where subatomic particles moving at near light speed live much longer than their stationary counterparts before decaying. The universe imposes a cruel trade. Travel fast enough, and you can reach distant destinations within a human lifetime, from your perspective. But everyone you knew on Earth will be long dead when you arrive. You'd be traveling into Earth's future, emerging into a world centuries or millennia beyond your departure. There's no going back. This is why, even with unlimited energy for propulsion, interstellar colonization faces profound challenges. Astronauts become temporal exiles, severed from their origin civilization not just by distance but by time itself. The expansion of the universe raises questions about its ultimate fate. Will it expand forever? Will it eventually stop and collapse back? The answer depends on the total density of matter and energy in the universe. If the density is high enough, gravity will eventually halt the expansion and pull everything back together in a big crunch, a reverse of the Big Bang. If the density is too low, the universe will expand forever, becoming increasingly dilute and cold. There's a critical density where the universe is balanced between these extremes. Measurements suggest the universe is very close to this critical density. But there's a twist. The expansion isn't slowing down as you'd expect if gravity was the only factor. It's accelerating. Discovered in 1998 by studying distant supernovas. The discovery was so unexpected that it was initially met with skepticism, but further observations confirmed it. The universe's expansion is accelerating. Something is pushing space apart, counteracting gravity. We call this dark energy. We don't know what dark energy is. It might be a property of empty space itself, a cosmological constant that Einstein had proposed for different reasons. Or it might be a dynamic field filling space. Either way, dark energy makes up approximately 68% of the total energy content of the universe. Dark matter is around 27%. Ordinary matter, everything we can see, is only roughly 5%. The universe is dominated by things we don't understand. The acceleration has been going on for approximately 5 billion years. Before that, the universe's expansion was decelerating due to gravity. But as the universe expanded, matter became more dilute. Gravity's influence weakened. Dark energy's influence remained constant, or possibly even increased. Eventually, dark energy took over, and the expansion started accelerating. In the far future, the acceleration will continue. Galaxies beyond our local group will be pushed beyond our cosmic horizon. the observable universe will shrink. Eventually, in trillions of years, the only galaxies visible will be those gravitationally bound to our local group. The rest will have been carried away by the expansion of space. Even our local group won't last forever. In the far, far future, quadrillions of years from now, stars will stop forming. All the gas will have been used up or expelled from galaxies. Existing stars will burn out. White dwarfs will cool into black dwarfs. Neutron stars will remain. Black holes will slowly evaporate through Hawking radiation. Eventually, the universe will be dark and cold, filled with black holes, dead stars, and elementary particles spreading through ever-expanding space. Even black holes will eventually evaporate, leaving only a sea of photons and other particles spreading through ever-expanding space, the heat death of the universe. The ultimate fate predicted by thermodynamics and general relativity combined, but that's trillions upon trillions of years in the future. For now, the universe is vibrant, stars are forming, galaxies are colliding and merging, black holes are growing, and we're here, on a small planet, trying to understand it all. General relativity gives us the tools to understand gravity at every scale, from falling apples to the expansion of the universe. A remarkable achievement. Space exploration faces fundamental limits. The nearest star is over 4 light-years away. Even at 10% of light speed, far beyond current technology, the journey would take over 40 years. Accelerating a spacecraft to half-light speed would require energy equivalent to all electricity humanity generates in a year, just for a gram-mass probe. For a craft carrying people, the energy requirements become astronomical. Nuclear propulsion, antimatter engines, light sails, generation ships, all have been proposed. All face enormous challenges. Maybe interstellar travel with humans isn't practical. Maybe we're confined to our solar system. That's not necessarily bad. The solar system is vast, with plenty to explore. Mars could be terraformed over centuries. Jupiter's and Saturn's moons harbor subsurface oceans that might contain life. Asteroids could be mined for resources. Space habitats at Lagrange points could house millions in Earth-like conditions. The solar system could support a civilization far larger than Earth's current population, spreading across billions of kilometers while remaining connected by light-speed communications measured in hours, not years. There's something profoundly lonely about the idea that every star might be forever beyond our reach, that we might be observationally isolated, not because life doesn't exist elsewhere, but because the distances are too vast and the speed of light too slow. General relativity tells us the universe operates on scales far beyond human comprehension, placing fundamental constraints on what's possible. Yet there's also beauty in this. It means every moment is precious. We're here briefly, but in that time, we can understand. We can measure space-time curvature, detect gravitational waves from colliding black holes billions of light-years away, image supermassive black hole shadows, trace cosmic history back to the Big Bang's first moments. We're tiny creatures on a small planet who have figured out fundamental laws governing cosmic-scale phenomena. Extraordinary. Gravity connects everything through the elegant geometry of curved space-time. It shapes planets and stars, binds galaxies, drives cosmic evolution. Understanding it through general relativity is one of humanity's greatest intellectual achievements. Centuries of observation and thought, from Galileo to Kepler to Newton to Einstein and countless others, testing, measuring, refining. Yes, gravity limits us. It makes interstellar travel incredibly difficult, constrains how fast we can go. But it also enables everything. Without gravity, stars wouldn't form. Planets wouldn't exist. The universe would be a thin gas spreading through space forever. No structure, no complexity, no life. Gravity is why the universe is interesting. Why we're here. Mysteries remain. Dark matter and dark energy comprising 95% of the universe. Quantum gravity, the very early universe. Black hole interiors. But general relativity provides the foundation. Future discoveries will build on it, extending our understanding to new realms. The core insight that gravity is space-time curvature, not a force, will endure as a fundamental truth about how the universe works. Until next time, keep looking up, keep questioning, keep seeking to understand. The universe is vast and complex, but it's also comprehensible. We can figure it out. We are figuring it out. And you're part of that journey just by trying to understand. Thank you for watching. And remember, you're not being pulled down by gravity. You're following a geodesic through curved space-time. You're surfing the geometry of the cosmos. How cool is that?